Thank you for having me. It's very nice to have this opportunity to tell you a little bit about my work, especially in a department that brings together so many different cognitive science perspectives and methods and disciplines. And I'm hoping I can add to that with the kind of work that I'm doing. I'm particularly interested in why people are so different. And I focus on children's differences in particular. Children differ in a wide range of domains. They differ in height. Some are funny, some are not so funny. Some learn quickly, some don't learn so quickly. And the question for me is, where do these differences come from? And what do we do with them? How do we best respond to those differences? I focus on school performance in particular because school serves two very important functions in society. Some people say it is the most expensive and largest social intervention that we afford as societies, because we ask children to go to school for about 10 years in Western countries at least. And what we hope them to achieve by going to school is to learn the knowledge and skills that they need to utilize the opportunities that society affords them, to participate in society, to become productive members of society. But school also has a gatekeeper function. So people who do well in school then tend to be recommended for further education. The ones who don't do so well in school tend to not be recommended for further education. And education happens to be the one thing that affects all of our developmental life outcomes. So the degree to which you're educated affects how healthy you are, how happy you are, how much money you earn, and even how many children you have. So that's why I think thinking about school performance is fundamentally important, because it has such a far reach on our life's developmental differences. Now, children's differences in school performance are evident early on. They're vast, and they occur all around the world. This is data from PISA. PISA is an international assessment exercise that's conducted every few years on all 15-year-olds around the world in representative samples. And what you see on the left here are all the different countries that data were collected from. And the plot shows you the extent to which children vary in each country between the lowest performing ones on the left and the highest performing ones on the right. Now, some people are very interested in the mean differences between countries. And I'm sure you've seen the newspaper reports that say, usually England does bad in PISA. It's like, England, third place in PISA in Europe. That should not happen. We should be higher on average. But the average is not very informative if we think about how vastly different children do in this test in all countries. And what I'm interested in is finding out why these differences occur. Why are they so different? What are these factors that apply across countries for children to do so differently well in school? And you might reasonably think a first point to start with is actually school, or the different kinds of school, or the quality of schooling that children experience. And as coincidence wants it, England is very famous for its different schooling systems. So this is a photograph that sums up the two-tier system that we have in schools. We have selective schools, where children are admitted either on the basis of passing a cognitive exam, and if you do well in the exam, you get to go, or your parents pay tuition fees, i.e. it's a private school that charges for the education, and so parents who have the resources can afford sending their children. And so the two boys on the left that you see here, they attend a school that's called Harrow. It's one of the most famous boarding schools in the United Kingdom, where people pay a lot of money to send their children. And on the right, you have a bunch of boys who attend a non-selective state school, meaning everyone can go. You don't have to pay money. You don't have to pass a cognitive exam. You can just attend. And so the question becomes, if you go to a school that you pay a lot of money for and that children are selected into on the basis of their cognitive abilities, will that school help you to do better? Will you learn more in such a school? Will your exam grades be better, and therefore your chances at life? And we had the chance to look at that with some empirical data in a recent cohort. So in children born in the mid-90s, in a population representative sample, where we looked at their school leaving grades. So these are the grades that children earned in exams at age 16 at the end of compulsory schooling. So the gray bar on the side are non-selective state schools. All children can go. The two blue bars are the selective schools. The lighter one is so-called grammar schools. These are schools that admit children after they've performed in a cognitive test. And the dark blue one is the private schools, which funnily enough in England are called public schools, but that's just to confuse the listener a little bit. And the private schools charge tuition fees. And if you look at the difference in the bars, you can see that the children in the grammar and private schools do much better in the school leaving certificates than the children in the state school. So looking at that graph, you might think, going to private school does add value. It makes my children do better, and therefore it's wise to invest in this. But these are obviously not the same populations of children who attend these different types of schools, but they have been selected on cognitive ability and essentially family background. So if we control for these two variables, if we ask how clever are these children on average and how rich are their parents, that happens to the graph. So the significant difference in exam performance goes away, which suggests ultimately that it's not schools that drives children's differences in performance. It's something else. It's something that they already bring to school, and that is likely to have to do with their family background. I should add here to make the point why the selection effect is so strong. On average in the United Kingdom, boarding school or private school costs £16,000 a year. The average income, the average household, disposable household income is £32,000 a year. So that gets to tell you what proportion of the population can actually afford sending their children to one of these selective schools. Family background comes in many different ways and forms and has many different aspects. There are families like these, and there are families like these. And if we think about family background in research, we try to extract systematic differences that we can observe between families. And we usually focus on the rearing environment that families provide for their children. So one thing we tend to ask about is the family home that children grow up in. Is it big enough that does everyone have a room? Is it crowded? Is it chaotic? Is it loud? Is there space for children? We ask about the things that children have. Do you have toys? Do you have books? Do your parents engage with you in an intellectually stimulating way? Do they read to you? Do they discuss things with you? And we might think about the wider neighborhood or environment. Is it safe where you grow up? Is there access to green space? Are there good schools in the neighborhood? And all of these things are associated with family background and the sort of rearing environment that families provide. But there's something else that families also give to their children, and that is the DNA differences that they pass on. So it's the genetics that children inherit from their parents. And what I'm particularly interested in is bringing these two factors together, or to be precise, to disentangle them and think about how genetics and environments influence children's differences in school performance. Why genetics? Why is genetics a good question? Genetics is a good question because everything is genetic, in the way that the first law of behavioral genetics says all traits are heritable. And what that means is that all traits that differ between people in a population, a proportion of those differences can be attributed to people's genetic differences. So it's a population-based statistic. It's not an individual level statistic. It doesn't mean that half of you is genetic and half of you is environmentally driven. It means that in the traits where we observe differences between each other, let's say height or school achievement or sense of humor, a proportion of those differences is due to our genetic differences. And we know this from basically more than a century of twin and family design studies, where we use the differing degrees of genetic relatedness to see differences in phenotypic resemblance. And the best example for illustrating that point is comparisons between monozygotic and dizygotic twins. So monozygotic twins are identical. They share 100% of their genes. We call them genetic clones because they come from the same egg and the same sperm, and then they divide during the pregnancy early on, and you have two genetically identical children. Dizygotic twins come from 2 eggs and 2 sperms, so they're genetically as similar as any other fraternal siblings, and they share on average 50% of their segregating genes. And if we find that 2 monozygotic twins are more similar to each other in a trait than dizygotic twins, we have to conclude that there are genetic influences on that trait. Because the thing that makes the 2 types of twins different is the degree of genetic resemblance. And a few years back, Tinka Polderman from the Freie Universität in Amsterdam undertook a massive review to bring together all the literature that has used family and twin studies and estimated heritability of traits. And so what you see here is all the traits that they found studies that people have estimated heritability for. So you have skeletal here, which is things like height and arm length. You have cognitive traits here, which is school performance or executive function or cognitive ability. You have psychiatric traits, so mental health-related traits, schizophrenia, depression, and then you have social values and even social interactions near the end. So you have the whole range of phenotypes in which humans differ. And what you see plotted are different types of heritability and environmental influence estimates on the population level. The focus is on the dark purple bars, so these are always on the outer left side, which are the estimates of heritability, i.e. the proportion of variance in each trait that can be attributed to people's differences, people's genetic differences. And if you eyeball this, and I ask you to draw a line through all the dark purple bars, approximately, I hope you agree with me that it falls somewhere there. And that is the 50% mark, meaning that on average, half of our differences in phenotypic traits can be attributed to our genetic differences, say twin and adoption studies. Now, that's a very good starting point to think about what are these genetic variants that drive our differences. And whilst twin studies have been around for more than 120 years by now, the ability to look at specific genetic variants or DNA that drives heritability has only become possible over the past 20 years. But what we can do now is conduct so-called genome-wide association studies, where we test associations between DNA variants and a target phenotype, a trait that we are interested in very large discovery samples. And then we can see which DNA variant is associated with that trait. So this plot here behind me, this is called a Manhattan plot because it allegedly resembles the skyline of Manhattan. And what you see plotted is at the bottom the chromosomes that we carry. So we carry 23 chromosomes in 2 copies. You may note that the 23rd one is missing. That's a sex chromosome, and these tend to not be included in genome-wide association studies. But you have the 22 chromosomes, and the red dots signify p-values. That is the p-value that's associated with the association between a DNA variant anywhere along the chromosomes and the target phenotype. The target phenotype in this case is years spent in full-time education. It's a course measure to reflect people's ability to learn. On average, people who have a greater ability to learn spend more time in full-time education. The reason that it's used is that you need very, very large samples in order to run this kind of analysis and identify DNA variants associated with years spent in education. And years spent in education is very easily collected as a data point in large population studies. So this graph shows you summary data from 1.1 million people and gives you an idea of the number of DNA variants that are significantly associated across our genome with years spent in education. You may see the dotted line here. that signifies genome-wide significance. So that's the p-value level corrected for multiple comparisons, above which a DNA variant is said to be significantly associated with the target phenotype. And what you can see from this is that we're talking about thousands and thousands of DNA variants. It's not just 1 or 2 genes that make a difference in how long you stay in education. It's not even just 100 or 1,000. It's many thousand. And that posits a certain challenge for genetics because it makes it very difficult to trace what the biological mechanisms are through which a DNA variant influences phenotypic behavior. But in a way around it, or an alternative approach, is to say, can we sum up all of these associations and use them in research? And that's exactly what polygenic scores do. They take those summary statistics from a very large discovery sample and then take an independent sample that has been genotyped, so you know their DNA variants, and see which ones they carry. And then basically you add together the alleles that a person carries that were identified before to play a role for years spent in education in the discovery sample. In your independent sample, you add them all together, and what you end up with is a so-called polygenic score. It's similar to a personality trait scale score. It's just adding items together that have been associated with a trait. And if you do that, you get a perfectly normally distributed polygenic score that you might want to think about as an index of the genetic propensity to learn. And it's very similar to the normal distribution that you get if you plot children's school grades. And what you can then do is you can use that score in studies in different ways. You can try and predict outcomes. You can try and disentangle the gene-environment interplay. You can test for gene-environment interactions. Or you can use it to control for genetic confounding when you're trying to identify environmental factors that cause change. Now, I'll first show you how we can use polygenic scores in the context of prediction. So this is one of the first studies that came out using the polygenic score for years spent in education to predict children's differences in school performance. So these are, again, end of compulsory school leaving grades. Children were 16 years old when they took these exams. These exams matter. They forecast if you go on to further study. So students in the UK spend a lot of time preparing for these exams. They're very serious. And what you see plotted here is on the left, the exam grades. They go from A+ to F, A+ being the best grade, F being a fail or the worst. And what you see plotted across is the sample broken down into deciles, so into 10% units of polygenic scores. So down here, you have the decile that scored on average lowest in polygenic scores. And on the other side, you have the decile that scored highest in polygenic scores. And what you can see is a linear relationship between the polygenic scores, so the genetic propensity for learning, and school grades. You can also see, I hope, that a lot of the dots don't quite fall into the boxes. So that's the heterogeneity around the estimate. It's definitely not a perfect correlation. We're accounting for 16% of the variance, so it's not that we explain all of it, but you see a very clear, straightforward trend that actually does translate in meaningful effect sizes. So the average grade in the lowest 10% is a C in school leaving certificates, and out of that decile, about 25% go on to university level studies. If you look at the highest decile, the average grade is an A-, and 75% go on to university. As I said, this was the first study, or one of the first in this, and I know many of you were very interested in replication and making sure that results are not spurious, so just very exciting for the moment. So what we're doing right now in my lab is meta-analysis of all the studies that have been published to date and used polygenic scores in the prediction of educational achievement or school grades. And Kirsty Wilding, one of my PhD students, is leading on that. And what you see here is plotted across birth years, all the cohorts that have been studied in that context. you have the polygenic score prediction, or the correlation between polygenic scores and school grades plotted on the left. This is not corrected for anything. This is just the raw correlations. The circle color represents the country that the samples were from. So you will note all of those come from so-called weird countries: Australia, Netherlands, Norway, the UK, and the United States. So it's a very Eurocentric research area. Populations are mainly drawn of European ancestry. You may also see that there are two types of shapes here. The circles are samples of European genetic ancestry, and the triangles are of African American ancestry. There are only 3 samples of African American ancestry, so it's not very representative of the world's population. And the circle size represents the sample size. So if you run a meta-regression on this, correcting for age of assessment and the sort of test type differences, you get an overall estimate, a meta-analytic estimate of 0.5, based on almost 84,000 individuals across 19 estimates or effect sizes. So that would be equivalent to a strong association between polygenic scores and children's school performance. So it does replicate. At this moment, I think it's important to say what genetic influence is not. That things are heritable or under genetic influence does not mean that they are innate, that you're born with them or you're not born with them. And the best example for that is the ability to read. Children learn to read, but they need to be taught. The ability to read is one, or differences in the ability to read is one of the most heritable traits that we know. So it's under strong genetic influence, and yet it requires environmental input. So to say something is heritable does not mean it's innate or born with. The second point is that heritability doesn't mean something is immutable. Just because something's under genetic influence doesn't mean you couldn't change it, or that it's set in stone in the population. All the estimates that we have are for a given population at a given time. If you change the condition of that population, if you change their environment, you would also change the genetic prediction. And what we're talking about when we interpret these estimates is probabilistic propensities. So there's a likelihood, a likelihood driven by genetics that some people will find it easier to learn in school than others. Some people will find it easier to learn new languages. Some people will find it easier to lose or to gain weight for genetic reasons. But it is probabilistic. It doesn't mean it has to be, and it doesn't mean that we couldn't change it if we wanted to. We might draw a parallel with school grades. School grades are used to predict how well you will do at university. On average, that works out, but we all know people who actually weren't very good at school and then did extremely well at university, and the same way around, people who performed excellently in school and couldn't handle much university or didn't get much out of it. So it's a prediction, it's a probability, it's not deterministic. And the last point is about heritability and its policy implications. There are no necessary policy implications that follow from heritability or finding genetic influences. The way we structure education systems, the way we make policies in education and anywhere else should be informed by the values of our societies and the ethics that we practice. And if it's really nice, we consider contemporaneous scientific evidence in that context. But finding heritable influences on children's differences in school performance does not mean that we need to change the education system or that there are direct recommendations that follow from it. We can think about it. We can consider if it's important. But it doesn't mean in one way or the other that we change how we educate people. Now, I want to show you one study where we really try to put together the traditional way of thinking about family background in terms of socioeconomic status and polygenic scores. And what we had here was a longitudinal study where we looked at children's school grades from age 7, 11, 14, and 16 years. And we plotted their associations between children's family background in terms of socioeconomic status, which here was parents' highest level of education, their highest their occupational prestige, and their income, and the polygenic scores of those children over time. And so what you can see is that already at age 7 years, the correlation with the socioeconomic status variables is slightly above 0.3, so that's a medium-sized stable association, and it increases as children grow older and go through school. So by age 16, we are looking at 0.45, almost a 0.5 association. You also see that the association between the polygenic scores and school grades increases over time, although on average it's lower, or in principle it's lower. It's just above 0.2 at age 7. It goes up to just to above 0.3 at age 16 years. Now, these two variables are not independent of each other, because parents' socioeconomic status is influenced by their genetics. Their occupational attainment, their educational attainment, and their income are also under genetic influences. And likewise, polygenic scores capture some environmental effects as a result of passive gene-environment correlations. So parents who provide the rearing environment for their children do so in line with their own genetics and with their children's genetics. The child has no influence on that. And that's what's called a passive gene-environment correlation. The child did not make a contribution to that, but their genetics align with the environment that the parents have created simply because they share the genes of their parents. And that means that both markers here, polygenic scores and socioeconomic status, should not be considered like opposing factors of nature versus nurture, but they overlap. They have common variance. And in fact, they correlate 0.35. So that's something to keep in mind. Socioeconomic status is environment plus its heritability, and polygenic scores are genetic variance, but also the passive gene-environment correlation that affects their development. Now, what we can do with this sort of data is think about different trajectories and the interplay between polygenic scores and socioeconomic status. So we split the sample into 4 groups because we wanted to see how those groups develop over time in school performance. So at the bottom here, you have the children who scored lowest in polygenic scores and also came from the most disadvantaged family backgrounds. That's the line in gray. In sort of turquoise, you have the children who came from who had the most advantaged family backgrounds and scored highest in polygenic scores. And then between, in orange, you have the children who scored low on polygenic scores but came from advantaged family homes, and the blue line is the children who came from the lowest SES families but scored relatively high in polygenic scores. And what you can see, or what I guess is one of the first things that you notice, is that the differences between the 3 groups are glaring already at age 7, and they widen as children go through school and get older. So by the time they're 16, the children who had the lowest genetic propensity for learning and came from the most disadvantaged families are far behind the children who had the highest genetic propensity and came from the most advantaged families. Some people say the most interesting story is in the 2 groups in between. The ones that have low genetic propensities and come from advantaged families and vice versa. And I find it usually depends on if you're a behavioral geneticist or a social scientist, which of the 2 groups you find most interesting. The behavioral geneticist wants to talk about the blue ones and says, see, genetics will out. If you have high genetic propensity for doing well in school, you will overcome the environmental disadvantages associated with your family home. The social scientist tends to focus on the orange line and says, family background is what pushes you over the line. Even if you're not naturally a good learner, if your parents support you, if they have the right resources at hand, if they have the money to pay for it, you will do well. Of course, both explanations are ultimately the same. It's just a toss of the coin which way you want to look at it. What you do see is that the 2 groups are significantly different. So the SES, the influence of family background as assessed in the traditional environmentally focused way, has a stronger effect than the polygenic scores, a stronger positive effect on school performance. Now, where does this leave us? What does this say about the utility of polygenic scores, or what we make of this kind of work? We can think about how it translates into real-life outcomes in terms of university admission. So these are similar numbers to the ones I've shown you before, but they're even more extreme because we're now considering the SES in addition to the polygenic scores. So in the lowest group, you have 21% of children going on to university. In the highest group, it's 77%. So these are substantial differences in university enrollment. We are currently in the UK at 38% of all 18-year-olds who enroll in university. So it's a relatively large proportion of the population. But I want to spend the remaining time of my talk to address three core contributions that I think polygenic scores can make to how we think about our education systems, how we do social science, and how we support children in their learning. So the first one is about how we structure education systems. Now, in putatively meritocratic societies like France or anywhere else in the West, we tend to emphasize equality of opportunity in education. We say as long as everyone has the same chance to go to school and to learn and to participate in education, their differences in outcomes are fair and justified because everybody had the same chance, and what you make of it is your contribution. But that's a bit of a problem if we know that children come with very different sets of skills and abilities to participate in education in the first instance. And it's a bit like this selection test, where the odds of doing well in it are very different depending on who you are or what kind of animal you are in this graph. So if you have children who have not learned the language that is practiced in education systems, who have never been to a classroom, who've grown up in families where education wasn't emphasized, the opportunities that primary school affords them are not equal to the children who've grown up differently. And that makes us wonder if equal opportunity is a good way of structuring education, because it ultimately increases inequality between children in educational outcomes. Or if we should reconsider this and emphasize equity in outcomes. Equity in outcomes would mean, for example, that we invest more support in children that are potentially weak learners or who struggle in school and help them close the gap towards the ones who are strong. But that would require a differential investment in children's education depending on their need, and people could argue that's not fair. You're giving more to some than to others. That is against the rule of equal opportunity. So it's a mixture between a societal and a philosophical problem. I don't have a good answer for it, but I thought I'd just put it out there. The second implication is for research itself. So the ultimate goal in behavioral science is to understand how DNA or the genome, the pathways of DNA and the genome through the brain, and how that affects our behavior or phenotypic development. And what we're trying to do is to identify biological causal mechanisms. I don't think polygenic scores are going to help us much in this, because they're very coarse summaries of genetic propensities. They don't lend themselves to identifying biological mechanisms. Instead, what they do is they bypass all the causal explanation part in the middle and go straight to prediction. Prediction and explanation are both important and valid goals in science. They tend to have different purposes. To explain something is important, but often independent of how well you predict it. So if I pick a random example from genetics, the BRCA genes 1 and 2 are known to cause breast cancer in women, but they're very rare. They only account for 1 or 2% of all breast cancers. So you cannot predict very well on a population level from it who will have breast cancer, but you know that the ones who carry well, unfortunately have very much increased odds. So there you have explanation versus prediction. What polygenic scores are good for is prediction, the potential to identify people at risk or at resilience. And that's where I think is the third contribution of polygenic scores, and that's one that lies a little bit in the future. So what you see here is genome-wide association studies as they have been published over the years, and the polygenic scores that could be created on the basis of them, and how well they predict educational outcomes. So the first genome-wide association study for years spent in education was in 2013, with a sample of close to 130,000 people. And everybody was terribly excited and thought, this is how we are finding the genes of education. And then that polygenic score that was calculated on the basis of those summary statistics, you see the unique sample estimates are in the two circles, accounted on average for 2% of the variance. And that was a bit of a bummer, because we thought we found the genes for education, and then you explain 2% of the variance in years spent in education, and that's not much. That is far behind of the heritability estimates from twin studies that came in at 50%. So then the next GWAS came along. The sample size was almost 300,000, and that was published in 2016, so 3 years later, and now we explain more of the variance, but still not massive. But it was a first hint that increasing the sample size will be the key to identifying more and more of the DNA variants that actually drive heritability. 2018, the largest GWAS for which summary statistics are available to date, 1.1 million people. And now, for the first time, we reach a prediction level of above 10%. The latest GWAS was published in 2022. It's more than 3 million people, and we are at 12% of the variance in years spent in education. So this is not school grades. This is always years spent in education, which is the target phenotype of the genome-wide association studies. So what you can see here is that as you increase GWAS sample size, you increase the precision of the prediction of the polygenic scores. And if we think about that, we will have even larger genome-wide association studies in the future. There is a possibility that someday we will have a polygenic score that would allow us to identify relatively reliably which children might struggle in school and which may not, and therefore introduce support and help systems for them early on, ideally before they have developed harmful learning behaviors. Like they have learned that I'm not good at school, and so they're scared of doing homework, and they just don't do it for a long time, and then the problem exacerbates and it gets worse and worse. If we had an early warning system, and we might want to think about polygenic scores in that way, we could identify those children and teach them early and help them overcome their struggles in school. As I said, this is a potential future contribution. We are not there yet. We don't understand enough about polygenic scores and how accurate their prediction is. As I showed you before, we have the samples that we have and the populations this has been tested in are very limited and not very representative. But it's one way of thinking about going forward, and it's also an important point to make in why it's important to discuss this now. It's going to happen from 2013 to 2022. It's less than 10 years. We've gone up in prediction massively. The next one is coming, and we might want to start thinking about what we do with this information when it becomes available. Now, I want to leave you with this quote, which I think sums up what I ponder when I do this kind of work and when I present it. It's by Marie Curie, who is very close to us right now. And she said, "Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less." And with that, I thank the wonderful people who do this work with me, and I thank you for your attention, and I look forward to your questions.